focus of this section is rational functions. A rational function is simply one polynomial function that's divided by another. And because it uses the operation of division, and division by zero is a problem, you can already get a hint that these functions are not going to be quite as well behaved and nice as the polynomial functions. Here's an example of a rational function. Again, you can see we've written it as a fraction with the fraction bar being the division. Polynomial in the numerator, polynomial in the denominator. This is another very basic rational function, and this is also a rational function. The numerator may not be in the standard polynomial form, but if you remember how to FOIL, or do double distribution to multiply a binomial times a binomial, you can turn it into a trinomial. This is an example of something that's not a rational function. That's just a polynomial. There's no division by another polynomial. This one we do see a fraction, but the fraction is just made up of constants. We're not actually dividing by a polynomial in terms of x. So that's not going to be a rational function. And this one also is not a rational function because on the bottom, I don't have a polynomial function in terms of x. I have a constant. If the denominator's a constant, it's not a rational function. The graphs of rational functions may have asymptotes or points of discontinuity. And here's a refresher on those. An asymptote is a line that a curve approaches as it heads to infinity or negative infinity. Rational functions can have vertical, horizontal, or slant asymptotes. Rational functions will never cross or touch a vertical asymptote. They'll just get closer and closer to that line. Rational functions may cross a horizontal asymptote, but only in the middle of the graph. It will not cross a horizontal asymptote out to the far left or far right of the graph. And a point of discontinuity is commonly referred to as a hole in a graph. It's a point on the graph where the function is undefined, and it's going to be because there's a division by zero occurring there. So here's one example of a rational function. The blue dotted lines are the asymptotes, the lines that this curve is getting closer and closer to. It won't actually cross either of those lines, but the function itself is the red curve. Sometimes we draw the asymptotes, sometimes we don't. This graph has two vertical asymptotes, one at x equals -2 and one at x equals +2. You can have multiple vertical asymptotes. However, if you have a horizontal asymptote, you will have only one. In this case, it's the x-axis, which is the line y equals 0. This rational function has a vertical asymptote at x equals 2. It has a horizontal asymptote at y equals 1. And notice it has a hole or a point of discontinuity at x equals -3. That's because that value causes a division by zero error. So it does not exist, and therefore there's a hole in the function. This graph has a vertical asymptote, and it happens to be at x equals the cube root of 2. And it has a horizontal asymptote at y equals 0, which is the x-axis. And notice in this particular case, you can see that the function does cross the horizontal asymptote right in the center of the graph. However, out to the ends, you can see it's just approaching that asymptote. It will not touch or cross it out at the ends of the graph. Here's how you find the domain of rational functions. The domain is always going to be all real numbers except for the x values that would make the denominator equal to 0. That would cause a division by zero error. So in the case of this rational function, what value of x will make the denominator equal to 0? I can take the denominator, set it equal to 0, solve for x, and I have that value, x equals 3. Now my domain is all the values except x equals 3. On a number line, what I'm really trying to show is this. There would be an open circle at 3 because I am not allowed to equal 3, but any other number is fine. There's two ways that you can write this. The simplest way is just to say x does not equal 3, and you may see it by itself, or you may see it inside of set brackets. It's slightly more complicated to write it as an interval because you have to break it up into two parts. First, you name the portion to the left of your x value, round bracket at your x value because you're not allowed to equal it, and then you unite that with a second interval that describes the right side. So starting at 3 but not equal to 3, round bracket to infinity. To find the vertical asymptotes of rational functions, you have to pay attention to whether or not you have common factors in the numerator or denominator. I'll explain that a little bit more in a minute. But assuming you don't, you can find the vertical asymptotes by setting the denominator equal to 0 and solving for x. If there is a common factor in the numerator and denominator, you disregard the root that comes from that factor, but keep any other roots as vertical asymptotes. And because these asymptotes are vertical lines, they will always be written as x equals a equations, where a is a constant, just a number. You determine the horizontal asymptote of rational functions by comparing the degree of the numerator, remember that's the highest exponent that appears on the variable, to the degree of the denominator. So in this example, the numerator has degree n, and the leading coefficient, the coefficient of that term is a, and in the denominator we have a degree of m, and the leading coefficient is b. You decide what your horizontal asymptote is by knowing the following rules. If n is less than m, or if you like that better in plain English, if the degree of your numerator is less than the degree of your denominator, your horizontal asymptote is always the x-axis, which is the line y equals 0. If n equals m, meaning the degree of the numerator equals the degree of the denominator, your horizontal asymptote is made by starting as y equals, because it's a horizontal line, and making a fraction out of the leading coefficient of the numerator divided by the leading coefficient of the denominator, a over b. And finally, if n is greater than m, meaning the degree of the numerator is greater than the degree of the denominator, you don't have a horizontal asymptote. There will be a slant asymptote, but you don't need to worry about how to find that. And the last part of working with rational functions is being able to find their points of discontinuity. If your rational function has a common factor in the numerator and denominator, your function will have a hole, or in other words, be undefined, at the root that comes from that factor. Here's an example. You can see in g of x, I have a common factor in my numerator and denominator of x plus 2. This is going to result in there being a hole in the graph at the root from this factor. So take the factor, set it equal to 0, and solve for x. This tells me that at x equals -2, I'm going to have a point of discontinuity. Now the other factor in the denominator, the x minus 3, you would set that equal to 0 because that's going to be significant as well. That's going to give you your vertical asymptote. So that's how you tell the difference between a hole in the graph and a vertical asymptote.